There is a particular kind of object in our universe that doesn't behave like anything else. An object so dense that gravity overwhelms every other force we know about. So compact that the math we use to describe ordinary matter simply stops working at its center. So strange that even light, the fastest thing in existence, cannot escape once it crosses an invisible boundary in space around it. We call them black holes. And tonight, we're going to walk slowly through their true scale. Most people, when they imagine a black hole, picture something cosmic and enormous, maybe like a vast pit in space, swallowing everything around it. That image is partly right. But the actual range of black hole sizes in our universe is staggering. From objects only a few kilometers across to monsters larger than entire solar systems. From masses a few times that of our sun to masses tens of billions of times greater. The category of black hole covers a range of scales so vast that calling them all by the same name almost feels misleading. The smallest black hole we know of weighs about 3 times the mass of the Sun, with an event horizon small enough to fit inside a city. The largest black hole we know of weighs 40 billion times our Sun's mass, with an event horizon larger than our entire solar system. Between these extremes lies an entire bestiary of black holes, each at its own scale, each with its own particular strangeness. Tonight, we're going to start small, with the smallest black holes we know exist, and we're going to climb, slowly and patiently, all the way up, past stellar mass black holes, past intermediate mass black holes, into the supermassive realm where black holes anchor entire galaxies up to ultramassive territory, and eventually to the single largest black hole we've ever discovered. An object so vast that the numbers describing it stop having any real meaning to the human mind. This isn't a list of facts. It's a slow walk through scales that most people never have the chance to comprehend. Lie back, get comfortable. The universe contains things that should not exist by any ordinary standard. Tonight, we're going to look at them, one size at a time. Before we begin, if you find this kind of slow exploration calming, a like or subscribe really helps the channel grow. It's a small thing for you, but it matters a lot for me. Now let's start with the smallest, the stellar mass black holes. But before we get into the modern catalogue of known black holes, it's worth pausing for a moment to consider how recent our understanding of these objects actually is. The concept of an object so dense that light cannot escape it goes back further than you might think. In 1783, the English natural philosopher John Michell, a clergyman and amateur astronomer, wrote a paper proposing the existence of what he called dark stars. Michell reasoned, using only Newton's laws of gravity and the assumption that light was made of particles, that there could exist stars massive enough that the escape velocity from their surface would exceed the speed of light. Such stars, Michell argued, would be invisible. They would still exist, still have gravity, but no light from them could reach us. The idea was nearly 100 years before its time, anticipating much of what we now know about black holes, even though Mitchell's underlying physics was wrong. Pierre-Simon Laplace, the French mathematician, independently proposed the same idea in 1796, then quietly dropped it from later editions of his work, as the wave theory of light made the original calculations suspect. The modern understanding of black holes had to wait until Einstein's general theory of relativity in 1915. Within months of Einstein publishing the field equations, the German physicist Karl Schwarzschild, serving as an artillery officer on the Russian front during World War I, found the first exact solution. Working between calculations of artillery trajectories and battling a rare autoimmune skin disease that would soon kill him, Schwarzschild derived the geometry of spacetime around a non-rotating spherical mass. His solution included a mathematical singularity at a specific radius, now called the Schwarzschild radius, where the equations broke down in interesting ways. For decades, physicists treated the Schwarzschild solution as a mathematical curiosity. The conditions required to produce a physical object dense enough to lie within its own Schwarzschild radius were so extreme that nobody believed they actually occurred in nature. Schwarzschild himself died in May 1916, never knowing what his solution would eventually mean. In 1939, Robert Oppenheimer and his student Hartland Snyder published a paper showing that, according to general relativity, a sufficiently massive star, at the end of its life, could not avoid collapsing into a region of space within its own Schwarzschild radius. The collapse would be inevitable. Nothing could stop it. The star would, in modern terms, become a black hole. Oppenheimer's paper appeared on September 1st, 1939, the same day Germany invaded Poland. World War II started, and the physics community had other concerns. Oppenheimer himself was soon directing the Manhattan Project. The black hole collapse paper went largely ignored for decades. The term black hole itself was popularized by John Wheeler in the 1960s, though Wheeler always credited an unnamed audience member who suggested the phrase during a lecture. Before black hole, people used cumbersome terms like completely collapsed gravitational object or Schwarzschild singularity. Wheeler's adoption of the simpler phrase helped these objects enter popular consciousness. The first observational evidence for black holes came in the 1960s and 70s. Cygnus X1, the first stellar mass black hole identified, was discovered in 1964. The supermassive black holes at the centers of galaxies began to be inferred from observations of quasars and active galactic nuclei in the same period. By the 1980s, black holes had moved from theoretical curiosity to mainstream astronomy. Direct photographic evidence had to wait until the 21st century. The Event Horizon Telescope's image of M87 star in 2019 and Sagittarius A star in 2022 completed the journey from speculation to direct observation in just over 100 years from Einstein's field equations. That's the brief history. Now let's look at the actual objects. A stellar mass black hole is what's left when a massive star dies. Not just any star. Stars need to be at least about 20 times the mass of our Sun to end their lives this way. Smaller stars, including our own, have a different fate waiting for them. They expand into red giants, shed their outer layers in slow waves of gas, and leave behind dense cores called white dwarfs that gradually cool over billions of years. Bigger stars, but not big enough for black hole formation, leave behind neutron stars instead, which are dense beyond imagination, but not quite dense enough to collapse all the way down. Only the truly massive stars, the rare ones with enough mass to overcome every other resistance their interiors can muster, become black holes when they die. When a star this big runs out of nuclear fuel, what happens at the core is sudden and violent. For most of the star's life, the outward pressure of nuclear fusion pushed against the inward pull of gravity. As long as fuel was burning, the star stayed in balance. But when the heavier elements are forged in the core's later stages, the energy yield from fusion drops. Iron is the breaking point. When a massive star's core becomes iron, fusion stops producing net energy. The outward pressure collapses. The inward pull of gravity, suddenly unopposed, takes over. The collapse happens in seconds. The core implodes inward at speeds approaching 20% of the speed of light. The infalling matter rebounds, slamming back outward with enormous energy, and that rebound becomes the supernova. The outer layers of the star are blasted into space in a brilliant explosion that, for a few weeks, can outshine entire galaxies. The supernova scatters elements across light years. The atoms in your body that are heavier than helium were forged inside stars and dispersed by exactly this kind of explosion. But while the outer layers are being thrown into space, the core continues to collapse. The matter doesn't stop collapsing at the size of a planet. It doesn't stop at the size of a city. It keeps collapsing past the density of a neutron star, past every limit that any other state of matter can resist. As far as our physics can describe, it becomes a single point, a singularity. The singularity is, mathematically, a point of zero size and infinite density. Whether it's actually a point in physical reality, or whether it's something different that our math can't quite capture, we don't know. The general theory of relativity, which describes gravity at large scales, predicts a singularity. But we know general relativity breaks down in extreme density conditions. A complete theory of quantum gravity, which we don't yet have, might describe what's actually happening at the center. For now, we call it a singularity. Knowing the word is a placeholder for something we cannot yet describe. Around that singularity is a sphere we call the event horizon. This is the point of no return. Anything that crosses the event horizon, including light itself, cannot escape. Outside the event horizon, gravity is intense but escapable. Inside, every possible direction leads inward, toward the singularity. Even the direction we call time itself bends, until forward in time means closer to the center. The event horizon is not a physical surface. There's nothing there to touch. It's just a mathematical boundary defined by the geometry of spacetime around the black hole's mass. If you were falling toward a stellar mass black hole, you wouldn't feel anything special as you crossed the event horizon. You'd just keep falling. The transition from outside to inside would happen at a specific point in space, but you'd have no sensory experience marking it. You'd already be doomed before you noticed. What you would feel, on your way in, are tidal forces strong enough to tear apart any ordinary object. We'll come back to exactly what falling into different sizes of black hole feels like later. For now, just know that the smaller the black hole, the more brutal the approach. For a stellar mass black hole of about 10 solar masses, the event horizon is roughly 30 kilometers across, smaller than most cities. A region of space the size of a metropolitan area containing 10 solar masses worth of compressed matter. That's the density we're talking about. To put that in perspective, our Sun is a sphere about 1.4 million kilometers in diameter. If you compressed our Sun's mass into a black hole, the event horizon would be about 6 kilometers across. The mass would be exactly the same. The amount of stuff would be exactly the same. But the volume would shrink from filling a region the size of 1 million Earths down to fitting comfortably inside a small city. That's what happens when gravity wins. The matter inside the event horizon, before it reaches the singularity, is being crushed under conditions that have no analog in the rest of the universe. The pressure is beyond what any other process can generate. The density is beyond what any other state of matter can hold. We can't experiment on it. We can't observe it. The interior of a black hole is, by definition, sealed off from the outside universe forever. The closest known stellar mass black hole to Earth is called Gaia BH1. It sits about 1,560 light-years from us, in the constellation Ophiuchus. It was discovered in 2022 through the Gaia Space Telescope, which detected the wobble of a sun-like star being pulled by something invisible. The companion turned out to be a black hole, about 10 solar masses just sitting quietly in space, not actively eating anything, not announcing itself with bright accretion disks, just gravitationally tugging on its companion star, betraying its presence by the way the star moves. There are probably hundreds of millions of stellar mass black holes in our galaxy alone. Most of them we'll never detect. They don't emit light. They don't actively consume matter. They just drift, dark and silent, through interstellar space. Some are paired with stars like Gaia BH1. Some are solitary. The first stellar mass black hole ever identified was Cygnus X1 in the constellation Cygnus. It was discovered in 1964 as a powerful source of X-rays. We didn't immediately know it was a black hole. The X-rays come from gas being ripped off a companion star, swirling in toward the black hole, heating up to millions of degrees as it spirals inward. That heated gas emits X-rays before it crosses the event horizon. The X-rays are essentially the death rattle of matter, on its way into the black hole, the last energy released by atoms before they vanish forever from the visible universe. The companion star to Cygnus X1 is a blue supergiant called HDE 226868. It's a luminous, massive star with roughly 30 solar masses. The two objects orbit each other every 5.5 days, locked in a dance that has been going on for millions of years. The black hole is gradually pulling material off the companion star, creating the accretion disk that produces the X-rays. Cygnus X1 became famous in the 1970s when Stephen Hawking and Kip Thorne placed a now legendary bet about whether it was actually a black hole. Hawking, ironically, bet against the black hole interpretation on the grounds that if he was right, and Cygnus X1 wasn't a black hole, he would still have insurance against being wrong about all his other black hole research. Thorne bet for it. As evidence accumulated over the following years, it became clear Thorne was right. Hawking eventually conceded the bet in 1990, agreeing that Cygnus X1 was indeed a black hole. The agreed-upon prize was a 1-year subscription to Penthouse magazine, delivered to Thorne, much to the displeasure of Thorne's wife. The black hole at the center of Cygnus X1 is about 21 solar masses, with an event horizon roughly 60 kilometers across. It sits about 7,000 light-years from Earth. Even at that distance, it's one of the most studied black holes in the sky, because it's relatively bright in X-rays and because we can observe its companion star directly to study the dynamics. GRO J165540 is another well-studied stellar mass black hole, about 11,000 light-years from Earth. It's smaller than Cygnus X1, around 6 solar masses, with an event horizon less than 20 kilometers across. It rotates extremely fast, nearly at the maximum rate physics allows for a black hole. The matter spiraling into it forms an accretion disk, glowing hot in X-rays, while powerful jets of plasma blast outward perpendicular to the disk at nearly the speed of light. These jets stretch for light years. The jets are one of the most fascinating aspects of feeding black holes. Some of the matter that's spiraling toward the event horizon doesn't actually fall in. Instead, it gets caught up in the magnetic fields wrapping around the black hole and accelerates outward along the rotation axis, blasted into space at relativistic speeds. We see these jets in many active black holes. They emit radio waves, X-rays, and even gamma rays. The jets from supermassive black holes can extend for thousands of light years beyond their host galaxies, painting the cosmic background in particle beams. Even though the black hole is invisible by definition, the activity around it is some of the brightest stuff in the universe. This is what stellar mass black holes look like when they're feeding. When they're not feeding, they're invisible. The galaxy is full of them, hidden in plain sight. Other notable stellar mass black holes include V404 Cygni, an X-ray binary that goes through occasional outburst phases when it suddenly starts feeding more aggressively. M33X7 in the Triangulum galaxy is one of the most massive stellar mass black holes known, weighing about 15 solar masses. M82 Zone in the Cigar galaxy is an extreme X-ray source whose central black hole properties are still being debated. Here's a fact worth sitting with. There are probably hundreds of millions of stellar mass black holes in our own galaxy. Estimates suggest that the average distance to the nearest stellar mass black hole for any random point in the Milky Way is somewhere around 20 to 30 light-years. The closest star to us, Proxima Centauri, is 4.2 light-years away. The next closest, Barnard's star, is 6 light-years. Sirius is 8.6. Our nearest stellar mass black hole could be roughly 5 times farther than Sirius, completely invisible, completely unknown. What if such a black hole were on a trajectory that would bring it close to our solar system? The probability is incredibly low. Black holes, even hundreds of millions of them, are spread across an enormous volume of galaxy. The odds of any specific black hole approaching our solar system in any given million-year window are vanishingly small, but not zero. If a stellar mass black hole were to pass through our solar system, the consequences would depend on how close it came. A black hole that passed within a few light hours of the Sun would gravitationally disrupt the planetary orbits, ejecting some planets into interstellar space and altering the orbits of others. A pass within the orbit of Pluto would be catastrophic for the outer solar system. A pass within the orbit of Earth would likely mean direct disruption to our world, either through orbital changes that alter our climate or through direct gravitational tidal effects. The good news is that such an event is unlikely on any human timescale. The Milky Way is a vast volume of mostly empty space, with even hundreds of millions of black holes still leaving most regions black hole-free at any given moment. Statistically, our solar system has been free of close black hole encounters for the 4.5 billion years of its existence, and there's no reason to expect one in the next few billion years either. But knowing they're out there, in the silent regions between stars, drifting through the dark, is one of those facts that shifts your sense of cosmic context. The galaxy is not a peaceful, well-understood place. It contains hidden objects of extraordinary density and gravity, doing nothing in particular until something gets close enough. Each of these objects represents a different chapter in the story of how massive stars die. Each is a corpse in a sense, but a corpse with extraordinary properties. The dead star has not vanished. It has transformed into something even denser, even stranger than what it was during life. Let's grow bigger. The next category up is something astronomers have struggled to find for decades: intermediate mass black holes. These are black holes between about 100 and 100,000 solar masses. They're significantly larger than the stellar mass black holes that form from individual dying stars. But they're significantly smaller than the supermassive black holes that anchor galactic centers. For a long time, this middle territory was a kind of black hole desert. We knew the small ones existed. We knew the big ones existed. But the in-between sizes were strangely absent from our observations. This was a real puzzle. Black holes should grow over time, in principle. A stellar mass black hole could feed on its surroundings, slowly accumulating mass, and eventually become much larger. 2 stellar mass black holes could merge, doubling their mass instantly. Over the age of the universe, you'd expect a continuous distribution of black hole sizes, from the smallest stellar mass remnants up through the supermassive monsters at galactic centers. Instead, we saw a gap. Black holes seem to come in two distinct flavors, with very little in between. Why the gap? Several theories competed. Maybe intermediate mass black holes did exist, but were hard to detect because they weren't actively feeding and didn't emit obvious signatures. Maybe they really were rare, with the formation processes that produce stellar mass and supermassive black holes operating through different mechanisms that didn't easily produce middle sizes. Maybe most intermediate mass objects had been swallowed by the supermassive black holes of their host galaxies long ago, leaving only the survivors at the extremes. That's changing. In recent years, astronomers have found increasing evidence of intermediate mass black holes. The most famous example is HLX-1, in a galaxy called ESO 243-49, about 300 million light-years from Earth. HLX-1 weighs around 20,000 solar masses. Its event horizon is about 120,000 kilometers across, roughly 10 times the diameter of Earth. So an object that fits inside the orbit of Earth's moon, containing 20,000 solar masses worth of compressed matter. HLX-1 is unusual because it's not at the center of its galaxy. It's offset from the galactic core, sitting in a region where you wouldn't normally expect to find a massive black hole. The leading explanation is that HLX-1 is the surviving central black hole of a smaller dwarf galaxy that was consumed by the larger galaxy long ago. The dwarf galaxy got stripped down by tidal forces, but its central black hole remained, now embedded in the outer regions of the larger galaxy. This pattern of intermediate mass black holes being the corpses of consumed dwarf galaxies may be how many of them get to where they are today. Dwarf galaxies can have central black holes proportional to their size, and when bigger galaxies eat them, the black holes survive the merger. The question of how intermediate mass black holes form initially is still unsettled. They're too big to come from a single star's death, but they're too small to be the original seeds of galactic supermassive black holes. Some theories suggest they form when stellar mass black holes merge over long periods of time inside dense star clusters. Others suggest they're the cores of dwarf galaxies that have been stripped down by larger neighbors, leaving only the dense central black hole behind. Some, possibly, are primordial, black holes that formed in the very early universe from density fluctuations rather than from any star. Globular clusters are particularly interesting in this context. These dense balls of ancient stars, found in the outer regions of galaxies, contain hundreds of thousands of stars packed into small volumes. The dynamics inside such a cluster favor occasional black hole mergers. A stellar mass black hole forms when a massive star dies. It sinks toward the cluster's center due to dynamical friction. Other massive stars and black holes also sink. They collide, merge, and grow. Over billions of years, this process can build up a substantially more massive object at the center. Several globular clusters have been studied for evidence of central intermediate mass black holes. The cluster Omega Centauri in our own galaxy may host one. NGC 2808, another globular cluster, shows hints of unusual stellar dynamics consistent with a central intermediate mass black hole. Confirmation has been difficult because the gravitational signatures are subtle, and the alternative explanation, a dense concentration of regular stars, is hard to rule out. What we've learned recently is that these intermediate mass objects exist in greater numbers than we thought. The LIGO and Virgo gravitational wave observatories have detected several black hole mergers where the resulting object falls in the intermediate range. The merger, called GW 190521, detected in 2019, produced a black hole of about 150 solar masses. That's right at the lower edge of intermediate mass territory, formed from the merger of two smaller black holes that had themselves been the products of stellar deaths. GW 190521 was particularly dramatic. The two black holes that merged to create it had masses of about 66 and 85 solar masses. The 85 solar mass progenitor sits in what astronomers call the pair instability mass gap, a range of masses where stellar evolution theory predicts black holes should not form directly from collapsing stars. The existence of an 85 solar mass black hole already suggests something unexpected, possibly that it formed through an earlier merger of two smaller black holes, building up to the eventually observed mass. Each gravitational wave detection adds a data point. We've now detected dozens of black hole mergers since the first detection in 2015. Many produce final black holes in the upper stellar mass range, but some are pushing into intermediate territory. Over the next few decades, as gravitational wave observatories become more sensitive and as new ones come online, we should detect many more, slowly building a complete census of black hole sizes. We're filling in the desert, one detection at a time. Before continuing the climb, gravitational waves deserve a section of their own, because the detection of black hole mergers has revolutionized our understanding of these objects in the last 10 years. For most of physics history, we observed the universe through light. Telescopes captured photons of various wavelengths, from radio waves to gamma rays, and the entire history of astronomy was the history of better and better light-gathering instruments. But Einstein's general theory of relativity predicted another way the universe communicates, through ripples in spacetime itself. When massive objects accelerate, they distort the fabric of spacetime around them. Those distortions propagate outward at the speed of light, like ripples spreading on a pond after a stone is thrown in. For ordinary masses, moving in ordinary ways, the resulting gravitational waves are absurdly tiny. Earth orbiting the Sun produces gravitational waves, but they carry away so little energy that no instrument we could ever build could detect them. Einstein himself thought gravitational waves might be unobservable in principle. Just like he initially thought gravitational lensing might be undetectable. He was wrong about both, but it took 100 years to prove it for gravitational waves. The first direct detection of gravitational waves came on September 14, 2015, by the LIGO experiment. LIGO, the Laser Interferometer Gravitational Wave Observatory, consists of two enormous L-shaped detectors, one in Hanford, Washington, and one in Livingston, Louisiana. Each detector has arms 4 kilometers long, with laser beams running down the arms and reflecting off mirrors at the ends. The interferometers are sensitive enough to measure changes in arm length smaller than 1/10,000th the width of a proton. The signal that arrived on September 14, 2015, was a passage of gravitational waves from the merger of two stellar mass black holes about 1 billion light-years away. The signal lasted for less than a quarter of a second. During that time, the two black holes had spiraled around each other and merged into one, releasing energy equivalent to 3 solar masses worth of mass energy in the form of gravitational waves. For a fraction of a second, the merger was the most energetic event in the observable universe, briefly outshining the combined light of all the stars in all the galaxies put together. The two black holes had been about 29 and 36 solar masses. The merged result was about 62 solar masses. 3 solar masses in mass had disappeared. That mass had become pure gravitational radiation, propagating through space at the speed of light, eventually reaching Earth a billion years later as the faintest possible jiggle in our laser interferometers. The detection was confirmed independently at both LIGO sites, with the signal arriving at Livingston about 7 milliseconds before Hanford, consistent with the wave passing through Earth in a specific direction. The shape of the signal, with its rising frequency and increasing amplitude before a final ringdown, matched theoretical predictions for binary black hole mergers with extraordinary precision. The Nobel Prize in Physics in 2017 went to Rainer Weiss, Barry Barish, and Kip Thorne for the development of LIGO and the first detection. Since then, LIGO and its European partner Virgo have detected dozens of black hole mergers. We now have a real catalogue of black hole binary systems, observed not through their light, but through their gravitational radiation. The catalogue includes mergers across a range of masses, from a few solar masses to over 100 solar masses. Each detection confirms general relativity in increasingly extreme conditions and adds to our census of the universe's black hole population. What's remarkable about gravitational wave astronomy is what it tells us that light astronomy cannot. Black hole mergers don't necessarily produce any electromagnetic radiation. Two stellar mass black holes that merge in interstellar space with no surrounding gas to be heated would be completely invisible to traditional telescopes. They could merge, and we'd never know, except for the gravitational wave signal. Before LIGO, we had no way to observe these events. Now we observe them roughly weekly during observation runs. The data suggests black hole mergers are surprisingly common. Many of the detected events involve black holes more massive than astronomers expected from stellar evolution alone. The merger, called GW190521, which I mentioned earlier, produced a final black hole of about 150 solar masses, the first clear example of an intermediate mass black hole forming through merger. Other events have shown black holes in the so-called pair instability mass gap, masses where stellar evolution theory says black holes shouldn't form directly. These observations suggest the universe is more complex than our models, with multiple pathways to black hole formation that we're only beginning to understand. Gravitational wave astronomy is also opening up the possibility of detecting much larger mergers. Future detectors like LISA, the Laser Interferometer Space Antenna, planned for launch in the 2030s, will have arms millions of kilometers long, sensitive to gravitational waves from supermassive black hole mergers. When two galaxies merge, their central supermassive black holes eventually fall together and merge as well, releasing enormous gravitational wave signals. LISA should detect these mergers across the observable universe, providing a complete census of supermassive black hole growth through cosmic history. We're at the beginning of an entire new way of seeing the universe. The first 100 years of black hole understanding gave us theory and indirect detection. The next 100 will give us direct detection of the most extreme events in the cosmos, in a frequency range that no light telescope can match. This is the latest chapter in the story of our growing understanding. Each black hole merger detected adds a tiny piece to the puzzle. Each one confirms general relativity in an extreme regime. Each one tells us that the universe contains more black holes, more mergers, more invisible energy releases than we previously knew. Even larger still are the supermassive black holes. Supermassive black holes are an entirely different category of object. They're not the corpses of dead stars, they're the gravitational anchors of galaxies, Every galaxy of significant size that we've ever studied appears to have a supermassive black hole at its center, including ours. The supermassive black hole at the center of the Milky Way is called Sagittarius A star. It sits about 26,000 light-years from Earth, in the direction of the constellation Sagittarius. Its mass is approximately 4.3 million solar masses. Its event horizon is roughly 24 million kilometers across, about 17 times our Sun's diameter. Let me say that again. 17 times the diameter of our Sun, but containing 4 million times its mass. That's the density. To put that 24 million kilometer scale in another framing, that's about 16% of the distance between Earth and our star. So, if you imagine the size of Sagittarius A star's event horizon and put it in our solar system, the entire black hole would fit comfortably inside the orbit of Mercury with room to spare. The whole thing, every kilometer of its event horizon, would be smaller than the inner solar system. We finally photographed Sagittarius A star directly in 2022 when the Event Horizon Telescope project released the first image of the central black hole of our galaxy. Before that, we knew it was there from indirect evidence. Astronomers had spent decades watching stars near the galactic center orbit something invisible. By tracking those orbits, they could calculate the mass of the central object. The orbital speeds were too high for the central mass to be anything other than a single supermassive black hole. The most famous of these orbiting stars is called STU. It orbits Sagittarius A star in about 16 years, completing one full orbit in less than a human generation. At its closest approach to the black hole, STU passes within about 120 astronomical units, which is roughly 4 times the distance from our Sun to Neptune. At that closest approach, STU reaches speeds of nearly 2.5% of the speed of light. The German astronomer Reinhard Genzel and the American astronomer Andrea Ghez, who led independent teams tracking these stars for decades, shared the Nobel Prize in Physics in 2020 for their work demonstrating that the center of our galaxy contains a supermassive black hole. Tracking STU and its sister stars required revolutionary advances in astronomy. Earth's atmosphere blurs the images of distant stars, making it impossible to resolve the individual orbits of stars near the galactic center using ordinary telescopes. To overcome this, Genzel's team at the European Southern Observatory in Chile and Gez's team at the Keck Observatory in Hawaii used a technique called adaptive optics. Special deformable mirrors in their telescopes adjust their shape thousands of times per second, compensating for atmospheric turbulence in real time. The result is images sharper than what an unmodified ground-based telescope could ever achieve, comparable in clarity to space-based observations. With adaptive optics, the teams tracked individual stars near Sagittarius A star year after year, watching them complete their orbits, some over decades, some over years. The orbital data revealed not just the existence of a massive central object, but its precise mass, 4.3 million solar masses. The data also revealed something more subtle. The orbits of the stars exhibit relativistic effects predicted by Einstein's theory. The closest stars precess in their orbits, meaning each successive orbit is rotated slightly compared to the previous one. This precession was predicted by general relativity and measured directly by tracking STU's orbit. The measurement is one of the strongest tests we have of general relativity in a strong gravity regime. Other stars near Sagittarius A star tell their own stories. 62 and S55 complete their orbits in just over a decade, getting even closer to the black hole than STU during their closest approaches. S02A, when it was first identified, briefly held the record for the closest known star to a supermassive black hole. Each of these stars is a probe of the space-time around our galactic center, and each one continues to confirm the picture. There's a 4 million solar mass black hole there, and the laws of physics around it work exactly the way Einstein predicted. The image, when it came, was both a confirmation and a strange thing to behold. A bright orange ring of glowing gas with a dark shadow at the center. The shadow is the black hole itself, where light gets bent around but cannot escape. We are now able to look directly at the heart of our own galaxy, and what we see is a hole. The gas around Sagittarius A star is hot but relatively quiet by supermassive black hole standards. Our central black hole isn't actively feeding aggressively. Most of the matter in its surroundings has been swept up long ago. What remains is a diffuse gas that occasionally provides small meals, producing brief X-ray flares that we detect from Earth. Sagittarius A star is by black hole standards a relatively calm specimen. This relative calm is unusual for a supermassive black hole. Many other galaxies have central black holes that are actively feeding, with bright accretion disks and jets that can be seen across cosmic distances. These are called active galactic nuclei, and the brightest of them, called quasars, can outshine entire galaxies. Sagittarius A star, by contrast, is dim. We had to wait decades and build a telescope as wide as the Earth to see it directly. The Event Horizon Telescope is not a Langlanguas's, a network of radio telescopes around the world, working together as if they were a single planet-sized instrument. Telescopes in Antarctica, Hawaii, Mexico, Spain, Chile, and elsewhere all observe the same target simultaneously. Their data is combined using a technique called very long baseline interferometry, which effectively creates a virtual telescope as wide as the distances between the participating sites. To photograph Sagittarius A star, the network needed near-perfect weather at every site simultaneously, exact synchronization of atomic clocks, and an enormous amount of computational processing of the resulting data. The image they produced is, in some ways, history's first photograph of the inside of our galaxy. There are roughly 5 different ways astronomers find and study black holes, and the methods themselves reveal how complex the detection challenge is. The first is X-ray observation. When a black hole has a companion star or surrounding gas that's actively falling into it, the infalling matter heats to millions of degrees and emits X-rays. Telescopes like Chandra and XMM Newton in space can detect these X-ray sources. This is how Cygnus X1 was discovered in 1964. X-ray observation tells us a black hole is feeding, even when the black hole itself is invisible. The second is stellar dynamics. Stars near a black hole, including supermassive black holes at galactic centers, orbit in ways that reveal the central mass. By tracking the orbits of multiple stars over years or decades, astronomers can calculate how much mass is concentrated at the center and over what region. The discovery of Sagittarius A star's mass came from this method, with Genzel and Gez tracking individual stars near the galactic center for almost 3 decades. The third is gravitational wave detection, which I just discussed. Mergers of black holes produce signals that travel through space-time and arrive at instruments like LIGO and Virgo. This method works for a specific subset of black holes, but it can detect events that produce no light at all. The fourth is gravitational microlensing. When a black hole passes between us and a more distant star, its gravity bends and amplifies the light from the background star, creating a brief brightening. By observing this brightening, astronomers can detect black holes that aren't actively feeding, and aren't paired with companions. The first definitively measured isolated stellar mass black hole was identified this way in 2022, found through a microlensing event lasting almost 3 years. The fifth is direct imaging via the Event Horizon Telescope. So far, this method has captured only 2 black holes, M87 star and Sagittarius A star. Each requires a planet-sized array of radio telescopes operating in coordination. Over time, this list will grow. Each method finds a different population of black holes. X-ray observation finds the active feeders. Stellar dynamics finds the stationary supermassives at galactic centers. Gravitational wave detection finds merging pairs. Microlensing finds isolated wanderers. Direct imaging finds the largest, nearest active black holes. To build a complete census of all black holes in the universe, we'd need to combine all 5 methods, plus possibly others we haven't yet developed. Estimates suggest there are about 100 million stellar mass black holes in the Milky Way alone, of which we've directly detected only a few dozen. The vast majority are simply invisible, drifting silently through interstellar space, emitting no signals we can detect. Our galaxy, like all galaxies, contains a hidden population of black holes vastly outnumbering what we observe. This is part of what makes the field so dynamic. Every time we develop a new method or a more sensitive instrument, we find more black holes. Each new detection refines our understanding. The catalog continues to grow. One of the most spectacular things black holes do, when they're caught in the act, is something called a tidal disruption event. Sometimes, a star wanders too close to a supermassive black hole. It doesn't fall directly in. It gets close enough that the black hole's tidal forces, the difference in gravitational pull from one side of the star to the other, exceed the star's own gravitational binding. The star is torn apart. Some of the material falls into the black hole. The rest is flung out into long streams of stellar debris. The whole event is called a tidal disruption event, or TDE. When a TDE happens, the central black hole brightens dramatically as it consumes the stellar material. From quiet, almost invisible, the black hole becomes the brightest object in its host galaxy for months. The flare is visible across the electromagnetic spectrum. Astronomers have caught dozens of these events with various wide-field surveys. A famous example is ASAS SN 14 Li, a tidal disruption event detected in 2014. A sun-like star wandered too close to the central supermassive black hole of a galaxy 290 million light-years away. The star was destroyed. The resulting flare brightened the host galaxy's center by a factor of hundreds. Astronomers watched it fade over months as the consumed stellar material spiraled into the black hole. These events tell us something profound about the relationship between supermassive black holes and their environment. The supermassives don't just sit there. Occasionally, when a star drifts too close, they consume entire stars in single events. The stellar material doesn't stay separate. It's mixed and added to the black hole's mass, contributing to its slow growth. If you're wondering whether such an event could happen near our own galaxy's central black hole, the answer is yes, but rarely. The current rate of tidal disruption events at Sagittarius A star is estimated at about 1 star every 100,000 years on average. So, somewhere in our galaxy's history, every 100,000 years or so, the central black hole consumes another star. The events have been happening since the galaxy formed, contributing to Sagittarius A star's slow growth from whatever mass it had originally. The visual of a TDE, if you could watch one happen at high resolution, would be extraordinary. A star approaches, gets stretched into spaghetti, and becomes a long stream of glowing matter spiraling into the black hole. Over weeks and months, the stream reaches the accretion disk, heats up, and emits brilliant radiation across multiple wavelengths. The black hole, briefly active, then quiets again as the consumed material is finally absorbed past the event horizon. These are some of the most violent events in the universe, and they happen somewhere all the time. Each year, several new TDEs are detected by sky surveys. The supermassives are not just sitting and growing slowly. They're occasionally devouring entire stars in spectacular bursts of activity. But Sagittarius A star is, by supermassive standards, on the smaller end. Many other galaxies host much larger central black holes. Andromeda, our nearest large neighbor, has a supermassive black hole estimated at around 100 million solar masses. That's about 30 times more massive than ours. NGC 1277, a galaxy in the Perseus cluster, has a central black hole of around 17 billion solar masses, despite being a relatively small galaxy. The relationship between black hole mass and host galaxy mass is one of the most studied questions in modern astronomy, because it tells us about how galaxies and their central black holes co-evolve. The galaxy Messier 87 in the Virgo cluster, about 55 million light-years away, contains a supermassive black hole that weighs in at around 6.5 billion solar masses, 6.5 billion times our Sun's mass. Its event horizon is roughly 38 billion kilometers across. That's about 250 times the Earth-to-star distance. The event horizon alone is larger than our entire solar system, out to about 5 times the distance to Pluto. Said differently, imagine standing on the surface of M87's central black hole. If a surface could exist there, light, traveling at 300,000 kilometers per second, would take about 35 hours, almost a day and a half, to cross from one side of the event horizon to the other. A single object, a defined region of space, larger than 5 solar systems lined up next to each other. The Event Horizon Telescope project photographed M87's central black hole in 2019, 3 years before they imaged Sagittarius A star. M87 was the first black hole ever directly photographed in human history. The image looks similar to the Sagittarius A star image, but represents a much larger object at much greater distance. The reason M87 was photographed first, before our own galactic center, has to do with practical observation challenges. Sagittarius A star, despite being closer, varies on much shorter timescales. The gas around it changes appearance over minutes. Imaging it requires capturing a single coherent moment, like trying to photograph a fast-moving object. M87, despite being 1,000 times more distant, has a much larger event horizon, so the gas around it changes more slowly. It was, in a sense, an easier subject for the planet-wide telescope network. Once they'd succeeded with M87, refining their techniques to handle the variability of Sagittarius A star took several more years. The black hole at the center of M87 is called M87 star, sometimes shortened to M87 asterisk. It's the active galactic nucleus of one of the largest galaxies in the Virgo cluster, which is the nearest major cluster to our own local group. M87 is an elliptical galaxy, much larger than the Milky Way, and contains roughly 1 trillion stars compared to our 100 billion or so. The central black hole is proportionally enormous, dwarfing what we have at home. What does it mean for something to be 6.5 billion times the mass of our Sun? It means that this single object contains more matter than entire small galaxies. It means that within a region of space larger than our solar system, gravity is so intense that nothing within it, no matter how energetic, can escape. The black hole is consuming matter from its surroundings, slowly, but its gravitational influence extends far beyond what's actively falling in. Stars, gas, and dust within the central regions of M87 all orbit this black hole. The galaxy's structure is shaped by it. M87 also produces one of the most spectacular relativistic jets in the visible universe. A bright streamer of plasma, about 5,000 light-years long, blasts outward from the central black hole at nearly the speed of light. The jet has been observed for over a century, since long before astronomers understood what was producing it. Heber Curtis first noted it in 1918, calling it a curious straight ray. We now know it's matter being ejected by the magnetic environment around the supermassive black hole, accelerated to relativistic speeds. The jet glows in radio waves, visible light, X-rays, and gamma rays. It's one of the most studied jets in astronomy. The energy carried by these jets is enormous. The jet of M87 alone carries an amount of energy each second comparable to the entire luminosity of a small galaxy. This energy comes ultimately from matter falling into the black hole, but only a fraction of the infalling mass actually crosses the event horizon. Some of it gets caught up in the rotational energy and magnetic fields, accelerated outward and ejected back into space. The black hole is, in a real sense, regurgitating some of what falls in the form of these high-energy beams. The effect of these jets on the host galaxy is profound. They blow bubbles of hot gas through the galactic medium, pushing back against the inflow of cool gas that would otherwise feed both the central black hole and new star formation. This process, called active galactic nucleus feedback, is now thought to be one of the main mechanisms regulating galaxy evolution. Without supermassive black hole feedback, galaxies would grow much more rapidly, and the cosmic structure we observe wouldn't exist in its current form. Black holes, in this sense, aren't just passive consumers of matter. They actively shape their host galaxies through the energy they release. The entire structure of galactic evolution depends on the balance between matter falling in and energy blasted out. The largest galaxies have the largest black holes precisely because the central black hole's feedback regulates the maximum size the galaxy can grow to. There's a deep relationship between black hole mass and galactic mass that astronomers have measured across thousands of galaxies. The relationship is so consistent that it suggests the two grow together in lockstep throughout cosmic history. Imagine a black hole large enough that our entire solar system would fit comfortably inside its event horizon. From the surface, if there were a surface to stand on, you would see only blackness in every direction except up. The light of the surrounding universe, distorted and bent by the black hole's gravity, would appear concentrated into a small bright disk overhead. Beyond that disk, nothing. Just black, all around, all directions. That's what M87 looks like from the inside, more or less. Of course, nothing from the inside ever sends back any signal. Anything that crosses the event horizon is permanently part of the black hole. Whatever happens in there is forever sealed off from the rest of the universe. But even M87, with its 6.5 billion solar masses, is not the upper limit. Larger than M87, larger even than the giants of Andromeda and the Virgo cluster, are the truly ultramassive black holes. These are objects so large that they push the upper limits of what current physics says should be possible. Phoenix A is one of these. Located in the Phoenix cluster, about 5.8 billion light-years from Earth, It sits at the heart of one of the largest galaxy clusters known. The black hole at its center has been the subject of debate. Direct measurements based on stellar dynamics suggest a mass of around 5 to 6 billion solar masses. But theoretical models based on the cluster's energetics and the central galaxy's properties suggest the central black hole could be as massive as 100 billion solar masses. The actual mass is uncertain, and the difference between these estimates is enormous. But the upper-end models suggest Phoenix A could be one of the most massive black holes ever inferred. If the upper-end estimate is correct, the Schwarzschild radius of Phoenix A would be roughly 600 billion kilometers across in diameter. To put that in perspective, the distance from our Sun to Pluto is about 6 billion kilometers. Phoenix A's potential event horizon would be 100 times larger than that. It would be so large that light, traveling at 300,000 kilometers per second, would take about 23 days to cross it. 23 days, light, to cross from one side of a single object to the other. For another way of grasping that distance, Voyager 1, the most distant human-made object, has been traveling away from Earth since 1977. After almost 50 years, it's now about 24 billion kilometers from us. That's the most distant point any human creation has ever reached. Phoenix A's potential event horizon is 25 times wider than the distance Voyager has traveled in nearly half a century. Voyager could fly across the entire diameter of Phoenix A at its current speed. But it would take Voyager more than 1,000 years to cross from one side to the other. These numbers stop being meaningful in any human sense. We can write them down. We can compare them, but comprehending what they actually mean, the sheer presence of an object that potentially large, requires reaching beyond our usual frameworks. If Phoenix A really is on the upper end of estimates, it's bigger than star systems, bigger than star clusters. The event horizon alone would be larger than many entire structures we'd casually call big in the universe. Phoenix A also produces one of the most powerful X-ray cooling flows in any known galaxy cluster. The cluster surrounding it is so hot, with temperatures of millions of degrees in the central regions, that it would normally cool quickly and feed the central black hole at high rates. Some of that cooling happens, but the process is moderated by the black hole's own activity, which heats the surrounding gas and prevents runaway feeding. This balance between cooling-driven feeding and feedback-driven heating is one of the active areas of research in galaxy cluster astronomy. And whether Phoenix A really is at the upper end of its mass estimates or closer to the lower end, there's still another contender we can compare it to. The most clearly measured ultra-large black hole sits much further away from us. TON 618. TON 618 is a quasar located approximately 10.4 billion light-years from Earth in the constellation Canes Venatici. It's so distant that the light we see from it tonight left when the universe was only about 3 billion years old. It's an ancient object, peering at us from across most of cosmic history, and what makes it remarkable is what powers its quasar brightness. An absolutely enormous black hole at its center. TON 618 was first identified in 1957 during the Tonantzintla survey of bright objects in the northern sky. The catalog designation TON stands for Tonantzintla, the Mexican observatory where the survey was conducted. At the time, astronomers didn't yet know what quasars were. They were called quasi-stellar objects because they looked like stars in optical telescopes but had unusual spectra. It took years of follow-up work to recognize that quasars were actually extremely distant galaxies with bright active centers powered by supermassive black holes feeding on enormous amounts of matter. The current best estimate for TON 618's mass is around 40 billion solar masses. Some measurements suggest the number could be closer to 66 billion. Either way, it's the largest black hole known to humanity. The event horizon of TON 618 is about 390 billion kilometers across. Light takes about 30 days to cross it. It's larger than our entire solar system, out to about 40 times the orbit of Pluto. A single object, a single region of space with a defined boundary larger than the orbital extent of 40 solar systems lined up. The numbers, again, are difficult. 40 billion solar masses, 390 billion kilometers across. A month for light to cross it. Imagine a journey along the event horizon of TON 618. If you traveled at the speed of light, every second of your journey would cover 300,000 kilometers. After a minute, you'd have crossed 18 million kilometers. After an hour, more than 1 billion kilometers. After a day, nearly 26 billion kilometers, just under the radius of Phoenix A. After a week, you'd be 1/4 of the way across TON 618. You'd need to travel for 30 more days at the speed of light to reach the other side. The diameter of one black hole is a month-long journey at the universe's absolute speed limit. What does the universe look like from inside the event horizon of TON 618? We don't know. We can't know. The math we have suggests certain properties, but it breaks down at the singularity at the center. Our equations, which describe most of the universe so well, simply cannot tell us what's happening in there. The interior of a black hole is one of the few places in physics where we know our knowledge is incomplete. The universe has put up a wall, and we cannot see past it. TON 618 sits at the upper limit of what black holes can grow to under normal feeding mechanisms. Astronomers have proposed theoretical limits that suggest black holes should not be able to exceed around 50 billion solar masses in normal conditions. The reasoning has to do with the way matter falls into black holes. Above a certain mass, the accretion disk around a black hole becomes unstable and self-disrupts before more matter can fall in. The black hole's own radiation pressure pushes back against the infalling material, capping the growth rate. TON 618, at 40 to 66 billion, is right at that boundary. It's possible that even larger black holes exist, but discovering them requires conditions that may simply not occur in our observable universe. There are some objects that have been claimed to potentially be even larger, including a hypothetical object at the center of the Phoenix cluster that some researchers have estimated at over 100 billion solar masses, but the measurements remain uncertain. TON 618, with its well-measured 40 to 66 billion solar masses, is the current undisputed record holder for confirmed black hole mass. So this is where the climb ends. With TON 618, the largest black hole we know about, an object containing 40 billion times the mass of our Sun, hidden in a quasar from the early universe, its light reaching us across 10 billion years of cosmic distance. Now, let's pause and put this scale in real perspective. A stellar mass black hole has an event horizon about 30 kilometers across with a mass of 10 suns. TON 618 has an event horizon roughly 390 billion kilometers across, with a mass of 40 to 66 billion suns. The ratio between them is staggering. TON 618 is about 5 billion times more massive than a typical stellar mass black hole, with an event horizon 13 billion times larger. If a stellar mass black hole were the size of a marble, TON 618 would be the size of a sphere larger than our entire planet. That's the range of black hole scales in our universe. From marbles to planets. From small mountains to galaxies. Here's another way to grasp this. The diameter of an atom is about 1/10 of a nanometer, which is 1/10 billionth of a meter. The diameter of the Earth is about 13,000 kilometers, or 13 million meters. The ratio between an atom and Earth is roughly 1 to 130 quintillion. That's a vast scale ladder, going from the smallest unit of ordinary matter to the size of an entire planet. Now consider the ratio between a stellar mass black hole and TON 618. A stellar mass black hole event horizon, 30 kilometers. TON 618 event horizon, 390 billion kilometers. Ratio, 1 to 13 billion. The black hole scale ladder is enormous, but it doesn't quite span the same vast range as the atom to Earth ladder. Yet within just the category of black hole, we have a 13 billion-fold difference in size. If you imagine a stellar mass black hole as a single grain of sand, TON 618 would be a sphere larger than the United States. That's the comparison. A different framing. Our Sun has a diameter of about 1.5 million kilometers. A stellar mass black hole has an event horizon 30 kilometers across. So a stellar mass black hole is about 50,000 times smaller than our star in diameter. Now consider TON 618 with its event horizon of 390 billion kilometers. That's roughly 260,000 times our Sun's diameter. So TON 618 is about 13 billion times the size of a stellar mass black hole, a scale ladder of 13 billion. Within just one category of cosmic object, the black holes alone span a range of sizes greater than almost any other category we know of in the universe. And one more. This time in time rather than space, light travels 300,000 kilometers every second. To cross the diameter of a stellar mass black hole, light needs about 1/10 of a millisecond. A blink of an eye, but smaller. To cross the diameter of TON 618, light needs about 30 days. So the same beam of light, traveling at the same speed, takes roughly 25 trillion times longer to cross the largest known black hole than it does to cross the smallest. The ratio of crossing times spans almost as much as the ratio of sizes. These are the same kind of object. Both are black holes. Both have event horizons. Both warp space-time in fundamentally similar ways. And yet they exist at scales that are almost literally incomparable. And these objects are real. They exist right now, somewhere out there. Phoenix A is, at this very moment, sitting at the heart of a galaxy cluster 5 billion light-years away, slowly swallowing the matter that drifts close enough. TON 618, 10 billion light-years away, is a specific point in the universe where the laws of physics as we know them surrender. Sagittarius A star is, in this very moment, in the center of our own galaxy, about 26,000 light-years away, slowly turning, slowly waiting. The universe is full of these things. Hundreds of millions of stellar mass black holes in our galaxy alone. Every other major galaxy with its own supermassive at the center. Likely tens of billions of supermassive black holes in the observable universe. Each one a region of space where matter has surrendered to gravity completely. The universe contains scales that are difficult for any mind to hold all at once. Tonight we walked through one of those scale ladders, the black hole ladder, from the smallest stellar corpses to the unimaginable monsters of distant quasars. But we're not done thinking about this, because the strangeness of black holes is not just in their size. It's in the way they bend reality itself. Inside the event horizon, time and space behave in ways that have no analogy on Earth. Outside, time runs at one rate, Approaching the event horizon, time slows down relative to distant observers. At the event horizon itself, from the perspective of someone watching from outside, time stops. An observer falling into a black hole would, in theory, never quite be seen to cross the horizon. They would appear from the outside to slow down infinitely, to redshift into invisibility, frozen at the boundary. From their own perspective, they would cross immediately. This effect, called gravitational time dilation, is real and measurable even in much weaker gravitational fields. The GPS satellites that guide your phone's navigation have to be calibrated for time dilation effects because their clocks run at slightly different rates than clocks on Earth's surface. Earth's gravity, while tiny compared to a black hole's, still produces measurable time differences between locations at different altitudes. A clock on the top of Mount Everest runs slightly faster than a clock at sea level. The effect is small, microseconds per year, but it's been measured directly. Near a black hole's event horizon, the same effect becomes extreme. As you approach the boundary, the difference in time between your clock and a distant observer's clock grows without limit. At the event horizon itself, the ratio is infinite. From the perspective of someone in flat space far away, time at the event horizon stops entirely. Inside the event horizon, the geometry of spacetime is fundamentally different. The radial direction inward becomes time-like. The forward arrow of time, which always points toward the future for everything in the rest of the universe, instead points always toward the singularity for anything inside the event horizon. There is no escape, not because the gravity is too strong, but because all possible futures lead inward. This is not a metaphor. This is what general relativity, our best theory of gravity, predicts. And we've tested general relativity in countless ways, and it has never failed us. Imagine being inside a black hole, falling toward its singularity. You don't just fall through space, you fall through time. Every passing moment, every tick of your watch, brings you not just closer to the center, but closer to the inevitable end. There is no direction you can move that doesn't take you nearer the singularity. Up, down, left, right, forward, backward in space, all of those become equivalent. Only one direction matters. Toward the center, toward the future, toward the place where physics ends. Once you cross the event horizon, you have a finite amount of proper time before you reach the singularity. For a stellar mass black hole, this proper time is measured in microseconds. You barely have time to register what's happening before you're crushed into the singularity. For a supermassive black hole like Sagittarius A star, the journey from the event horizon to the singularity takes longer, perhaps several minutes of proper time. For an ultramassive black hole like TON 618, the journey could last several hours from the falling observer's perspective. Hours of subjective time inside an object whose event horizon takes light a month to cross. But during all of those hours of subjective experience, the rest of the universe outside is running at a different rate. From the perspective of someone outside, the falling observer never reaches the singularity. They appear frozen at the boundary, infinitely redshifted, eventually fading from observation entirely as their light becomes too long wavelength to detect. The frozen observer is, from the outside view, a kind of permanent feature of the black hole, slowly fading into invisibility over astronomical timescales. This is the strangest property of black holes, and it's true at every scale, from the smallest stellar mass remnant to TON 618. The interior is, in some real sense, a place where time itself has a destination. Time dilation deserves more attention, because it's where black hole scale becomes truly disorienting. The closer you get to the event horizon, the slower time runs for you relative to distant observers. This effect is much more dramatic for supermassive black holes than for stellar mass ones, simply because their event horizons are larger and the gravitational gradients are gentler at the boundary. Near the event horizon of a supermassive black hole like Sagittarius A star, an observer could spend, by their own time, what feels like a few minutes, while billions of years passed in the rest of the universe. Civilizations could rise and fall in the time it takes you to glance around. Stars could be born and die, galaxies could merge and reorganize, all while you experience only minutes. This is not science fiction. It's a direct consequence of general relativity. The math is solid, the predictions tested, and the implications are real. A black hole isn't just a hole in space. It's a hole in time. Imagine sitting near Sagittarius A star, not falling in, just orbiting at a distance close enough that time dilation becomes significant. You watch the universe outside your local frame run forward at impossible speed. Stars in the distant galaxy are flickering through their entire life cycles in seconds from your perspective. Your own galaxy, your own home, ages thousands of years for every minute you sit there. The future races past you while you barely move through your own time. This is what supermassive black holes do just by being there. They warp time itself. Different scales of black hole mean different intensities of this warping. Larger means gentler gradients but more total warping. Smaller means sharper gradients but in a smaller region. Every black hole is a temporal as well as spatial anomaly. And the bigger they are, the more strange the temporal effects become. Now, consider a thought experiment. What would happen to you, specifically, if you fell into black holes of different sizes? Falling into a stellar mass black hole like Cygnus X1 or Gaia BH1 would be over very quickly. Long before you reached the event horizon, the gradient of gravity from your head to your feet would become unbearable. At maybe 100 kilometers from the event horizon, you'd start to feel stretched. By 50 kilometers out, the stretching would exceed the strength of your body's tissues. You'd be torn apart, not just into pieces, but into long, thin streams of matter. Spaghettification, as physicists colloquially call it. Your atoms would still exist, but as a stretched line of plasma falling along the gravitational gradient toward the singularity, you'd be reduced to a ribbon of matter, brighter than anything you'd produced in life, because your atomic structure would be excited by the falling, and you'd add your radiation to the accretion disk for a fraction of a second before crossing the event horizon. From the outside, your fall would appear to slow as you approach the boundary. Your light would redshift toward longer wavelengths, and eventually you'd fade from observation. From your own perspective, the entire event from spaghettification to crossing the event horizon would take maybe a few seconds at most. Falling into an intermediate mass black hole like HLX1 would be similar, but slightly extended. The gravitational gradient would be gentler, so you'd survive a bit closer to the event horizon as a coherent body. You might get to within 1,000 kilometers of the boundary before tidal forces shredded you. The crossing would still be over quickly in your subjective time, but the slightly gentler approach might give you a few minutes to register what was happening. You'd still be torn apart, but your final moments would last longer. Falling into a supermassive black hole like Sagittarius A star, the experience changes substantially. The tidal forces at the event horizon of a 4 million solar mass black hole are mild enough that you'd cross the boundary as a coherent body. You wouldn't be spaghettified at the event horizon. You'd cross it, still alive, still aware. The gravitational tidal forces wouldn't kill you until you got much closer to the singularity, perhaps within a few thousand kilometers of the center. You'd have minutes of subjective experience inside the event horizon before being torn apart. From the outside, you would appear to freeze at the boundary, your light slowing and redshifting until you faded from view. From your perspective, the universe outside would race forward at impossible speed in the moments before you crossed the horizon, and then, after crossing, the outside universe would lose all meaning. You'd see only what was inside the event horizon with you, falling in the same direction. Falling into a supermassive like the M87 black hole would extend the inside experience further. The tidal forces are even gentler at the event horizon. You'd cross with no spaghettification, no immediate sign of anything wrong, except the fact that you were now inside. The total time from event horizon to singularity would be tens of minutes of your own time. Your last subjective hour would be entirely inside a black hole. Falling into Phoenix A, the experience would last hours. You'd cross the event horizon as a perfectly intact body. There would be no immediate sign of anything unusual at the boundary itself. Looking around, you'd see a strange darkness ahead and a small bright disk of distorted starlight behind you, gradually shrinking as you fell deeper. The tidal forces would still kill you eventually, but you'd have time. Hours of reflection before reaching the singularity. Hours of falling through a region of spacetime that no other observer has ever traversed. Falling into TON 618, the largest known black hole, the experience inside would last about a day and a half. 35 hours of subjective time falling through a single object, sealed off from the rest of the universe. During those hours, the universe outside would have evolved billions of years. Civilizations would rise and fall. Stars would be born and die. Galaxies would merge. None of it would reach you. You would be in your own private, final hours, separated from cosmic time entirely, falling slowly toward an end that physics cannot describe. This is what it means for an object to be the size of TON 618. It's not just big in space, it's big in time, long enough for an entire human lifetime to fit inside its falling geometry, more or less. Long enough that any observer entering it has effectively stepped into a private timeline disconnected from the universe outside. The bigger the black hole, the more time you have inside. The more strange the experience inside might be. The bigger the gap between inside time and outside time. This is the deepest scale we're touching tonight. The scale of duration. Not just of distance, but of subjective experience that gets strangely extended at the largest scales. The biggest black holes are not just the biggest spatial objects in the universe, they're objects where time itself has more room to stretch. There's another dimension to black hole scale: rotation. Most real black holes in the universe are not stationary. They rotate. The matter that fell into them carried angular momentum, and the resulting black hole inherits that rotation. A rotating black hole behaves differently from a non-rotating one. The geometry of spacetime around it is more complex. The event horizon is slightly oblate, flattened at the poles by the rotation. The interior structure includes additional features that don't exist for non-rotating black holes. A rotating black hole, called a Kerr black hole after the physicist Roy Kerr, who first described it mathematically, has a feature called the ergosphere. This is a region just outside the event horizon where spacetime itself is being dragged around by the black hole's rotation. Anything inside the ergosphere is forced to rotate with the black hole, regardless of its own velocity. You couldn't stay still in the ergosphere, even if you tried. The space itself is moving. The ergosphere extends from the event horizon outward, depending on rotation rate. For black holes spinning near the maximum rate physics allows, the ergosphere can be substantially larger than the event horizon itself. The region of dragged spacetime around a rapidly spinning black hole becomes one of its defining features. Inside the ergosphere, but outside the event horizon, you can still escape. light and matter can leave, but only after being forced to participate in the rotation for a while. There's a process called the Penrose process, named after the physicist Roger Penrose, by which energy can theoretically be extracted from a rotating black hole by exploiting the dynamics of the ergosphere. It's never been observed in practice, but it's a real prediction of general relativity. The fastest spinning black holes we know of rotate at about 99% of the maximum allowed rate. Some accreting black holes appear to spin even faster, getting incredibly close to the theoretical limit. The maximum rotation is set by general relativity itself. Spinning faster would create a naked singularity, which our current physics says should not exist. The frame-dragging effect of rotating black holes was experimentally tested in 2011 by the Gravity Probe B satellite. The satellite measured the way Earth's rotation drags spacetime around our planet, an effect predicted by general relativity called the Lentz-Thirring precession. Earth's rotation is laughably slow compared to a black hole's, and yet the effect was still measurable with sensitive enough instruments. For a rapidly spinning supermassive black hole, the same effect is dramatic. Space-time near the black hole is being whirled around like water in a vortex. For a black hole of about 10 solar masses spinning near the maximum rate, the frame-dragging effect at the event horizon would carry an observer around the black hole at a significant fraction of the speed of light, regardless of any thrust they applied. There's no way to remain stationary near a rapidly spinning black hole. You're forced to participate in the rotation. The geometry of space-time itself is moving. For a supermassive rotating black hole, the same effect operates at much larger scales. The frame dragging extends millions of kilometers beyond the event horizon. Stars near the central black hole of M87 are subtly affected by this rotation. Their orbital dynamics include components that come from the spinning black hole's drag on space-time itself. Astronomers have started to measure these effects in some cases, providing direct tests of general relativity in extreme conditions. Now, let me tell you about another structure around black holes, the photon sphere. Just outside the event horizon, light can travel in stable circular orbits. This region is called the photon sphere. Photons that enter it can orbit the black hole indefinitely, in principle, before either falling in or escaping outward. The photon sphere is the boundary between safe gravitational influence and definite consumption. For a non-rotating black hole, the photon sphere sits at 1.5 times the radius of the event horizon. For a stellar mass black hole, that's maybe 45 kilometers from the center. For TON 618, the photon sphere is about 300 billion kilometers from the center, just outside the event horizon. What you see when you look at a black hole image, like the Event Horizon Telescope photographs, is largely the photon sphere. The dark central shadow is the event horizon, but the bright ring around it is light orbiting the photon sphere, eventually escaping to your eye. Some of those photons have made multiple loops around the black hole before reaching you. The ring is, in one sense, a multiple exposure of the same light bending around the warped spacetime. If you stood at the photon sphere of a black hole, in a hypothetical situation where you could survive there, you'd see a strange image. Light from behind you, having traveled around the black hole, would reach you. The back of your own head would be visible in front of you, faintly. Light that takes a complete circuit through the warped space would create infinite copies of yourself, fading into the distance. You'd be staring at yourself, recursively, in an optical loop created by the geometry of space-time. These are real predicted features of black holes. The geometry produces visual effects that have no analog in flat space. And around the largest, most active black holes, The accretion disks of infalling matter add their own scale layer. The accretion disk of TON 618, in its quasar phase, must have extended for trillions of kilometers, glowing brighter than entire galaxies as matter spiraled inward. The disks of M87, of Phoenix A, of all the active supermassive black holes, are vast structures in their own right, often visible as bright structures in galactic images. The disks extend thousands or tens of thousands of light-years, glowing across multiple wavelengths, marking the slow spiral of matter into the central object. The black hole itself is just the central object. The full structure, including the photon sphere, the ergosphere if it's rotating, the accretion disk if it's feeding, and the relativistic jets if the geometry favors them, can extend across enormous distances. A single supermassive black hole, with its full apparatus of feeding and rotation, can dominate a region of space many light-years across. This is one more way scale matters. Not just the size of the central object, the size of its influence. There's one more property of black holes worth understanding before we step back from the ladder. Black holes don't last forever. For most of the 20th century, astronomers believed black holes were perfect one-way streets. Matter went in, nothing came out, and they would persist forever. Then in 1974, Stephen Hawking made a discovery that changed everything. He calculated, using a combination of general relativity and quantum mechanics, that black holes should actually emit a faint glow of particles. This radiation, now called Hawking radiation, comes from quantum effects at the event horizon. Pairs of virtual particles are constantly being created and destroyed throughout space. Near a black hole's event horizon, occasionally one of the pair falls into the black hole while the other escapes. From an outside observer's view, the black hole appears to be slowly emitting particles. The Hawking radiation is incredibly faint for any normal-sized black hole. The smallest stellar mass black holes emit radiation at temperatures of microkelvin, far below anything we could ever detect. The supermassive black holes emit radiation at temperatures even closer to absolute zero. For all practical purposes, Hawking radiation is invisible. But over enormous timescales, the radiation does cause black holes to lose mass very slowly. So slowly that for stellar mass black holes, a complete evaporation would take longer than 10 to the 66 years. Trillions of trillions of trillions of times the current age of the universe. The largest supermassive black holes would take longer still, 10 to the 100th power years or more. But they will, eventually, evaporate. In the deep future of the universe, after all stars have died, after even the white dwarfs and neutron stars have cooled to the cosmic background, only black holes will remain, slowly emitting Hawking radiation, slowly losing mass. As they shrink, they emit more strongly until the final moments of evaporation become explosive bursts. The very last black holes in the universe, hundreds of trillions of years from now, will end in flashes of high-energy radiation, scattering their final mass into a universe that has long forgotten everything else. That's the last act of the cosmic black hole drama, born in the deaths of massive stars or in the densities of the early universe, growing through accretion and merger, anchoring galaxies for billions of years. Then, slowly, evaporating into the void. The longest-lived structures in cosmic history eventually reduced to nothing. But the evaporation of black holes raises one of the deepest unsolved problems in modern physics: the information paradox. In quantum mechanics, information is conserved. If you describe the state of a physical system at one moment, you should in principle be able to reconstruct its earlier state from any later state. The information about what went into a system is preserved in the details of what comes out. This is one of the most fundamental principles in quantum theory. But Hawking's calculation of black hole evaporation seemed to violate this principle. The radiation emitted by an evaporating black hole, according to Hawking's original analysis, is purely thermal. It depends only on the black hole's mass and a few other simple parameters, not on the specific composition of whatever fell in. If you threw a book into a black hole, then waited an absurdly long time for the black hole to evaporate completely, the radiation that came out wouldn't carry any information about the book. The book's content would be permanently lost, not just hidden but actually destroyed. This violates one of the foundational principles of quantum mechanics. For decades, physicists have argued about this. Stephen Hawking himself, in 1975, argued that information really was destroyed by black holes, and quantum mechanics simply had to be modified to account for it. Other physicists, including Leonard Susskind and Gerard Hooft, argued that information must be preserved somehow, and Hawking's calculation must be incomplete. In 2004, after decades of debate, Hawking publicly conceded the information paradox bet, agreeing that information probably was preserved in some way, even if we didn't yet understand the mechanism. The current consensus among most physicists is that information is preserved, but exactly how remains unsettled. Several proposed mechanisms exist, including the holographic principle, the firewall hypothesis, and various versions of black hole complementarity. None has been proven definitively correct. The information paradox suggests that black holes are even stranger than they appear. They don't just hide information behind an event horizon. They challenge our deepest understanding of how the universe handles information at all. Resolving the paradox will probably require a complete theory of quantum gravity, which we still don't have. That's a strange way to think about scale. The biggest black holes contain the most information about whatever fell into them. The information might be vast. Every atom of every star and planet that has ever fallen in, recorded in some way. If the information is preserved, it sits at the event horizon, perhaps in some kind of holographic encoding. If it's not preserved, it's gone, taking with it potentially incalculable amounts of cosmic history. Either way, the largest black holes are repositories of cosmic memory at scales we can barely imagine. Now let me think about how we got here. How black holes at every scale come into existence in the first place. Stellar mass black holes form from dying stars. We understand that. We have detailed models. We can predict roughly how many should form per century in a typical galaxy. We've watched supernovae and inferred the formation of new stellar mass black holes from them. Intermediate mass black holes are still partially mysterious. We know they exist now, but how they form remains debated. The most likely answer is gradual merging of smaller black holes inside dense stellar environments. But the rate at which this happens is uncertain. Supermassive black holes are deeply puzzling. We see them at the centers of galaxies, even at the earliest cosmic times. Quasars, from when the universe was less than 1 billion years old, already host supermassive black holes of millions or billions of solar masses. How did they grow so big so fast? The standard model of gradual accretion doesn't work. Black holes can only consume matter at a certain maximum rate, set by the radiation pressure of the infalling material itself. At that maximum rate, the fastest a black hole can grow, it would still take longer than the age of the early universe to reach the masses we observe. Quasars themselves are part of the puzzle. The brightest objects in the universe, quasars are powered by supermassive black holes, consuming matter at the fastest possible rates. The brightest quasar known, J05294351, has a central black hole of about 17 billion solar masses, consuming the mass equivalent of one sun every day. The luminosity is so extreme that the quasar outshines galaxies. It's visible across most of the observable universe. The peak of quasar activity in the universe was about 10 billion years ago, when the cosmic web was younger and gas-rich, and the supermassive black holes at galactic centers had plenty to feed on. Since then, quasar activity has declined sharply. Most galactic centers now have black holes that are either quiet, like Sagittarius A star, or only mildly active. The bright phase has passed for most of them, but during the peak of quasar activity, the central black holes were growing fast. Quasars, from when the universe was less than 1 billion years old, already host supermassive black holes of millions or billions of solar masses. The James Webb Space Telescope has been finding galaxies in the early universe that already contain unexpectedly massive black holes. Quasars at redshifts of 7 or higher, when the universe was less than 700 million years old, are showing up with central black holes of 1 billion solar masses or more. So how did they get so large so quickly? One leading theory suggests direct collapse. In the very early universe, before any stars formed, vast clouds of gas might have collapsed directly into massive black hole seeds, skipping the stellar stage entirely. Those seeds, already containing tens of thousands of solar masses, would have grown into the supermassive black holes we see by accretion and merging over the following billion years. Another theory suggests primordial black holes from the very first moments after the Big Bang formed from density fluctuations in the inflationary universe. Some of those seeds could have grown into the giants we observe. Primordial black holes are an interesting category in their own right. If they formed in the first fractions of a second after the Big Bang, when the universe was extraordinarily dense, they could come in essentially any size. Some theoretical models predict primordial black holes as small as the mass of an asteroid, with event horizons smaller than an atomic nucleus. Others predict masses up to thousands or millions of solar masses, providing the seeds for the supermassive monsters at galactic centers. The smallest primordial black holes, if they exist, would have already evaporated through Hawking radiation by now. Black holes with masses less than about 10 to the 11 kilograms, roughly the mass of a mountain, would have completely disappeared in the 14 billion years since the Big Bang, ending in flashes of high-energy gamma rays. Astronomers have searched for these final evaporation gamma ray bursts, but haven't yet detected any clearly attributable to evaporating primordial black holes. The intermediate mass primordial black holes, from about 100 million kilograms up to several solar masses, would still be out there today. They could potentially explain some fraction of dark matter, the invisible mass that makes up most of the matter in the universe. Several research programs are actively searching for primordial black holes through microlensing surveys, gravitational wave detection, and other methods. So far, the evidence suggests primordial black holes can't be most of the dark matter, but some fraction remains possible. If primordial black holes do exist, they would be a relic of the very first moments of cosmic history, surviving for nearly 14 billion years to the present day. They would represent a category of black hole quite different from the ones formed from stellar collapse, not made from any star, but from the conditions of the early universe itself. A third theory suggests super-Eddington accretion, where black holes can briefly consume matter faster than the standard maximum rate by exploiting some specific geometry of the infalling material. If black holes could routinely exceed the standard rate by factors of 10 or more, the early universe's black hole growth becomes more explainable. These observations are pushing our theoretical models even harder. Whatever process created these early supermassive black holes had to operate quickly and on enormous scales, and we don't yet have a complete explanation for how it worked. The truth is, we don't fully know. The largest black holes we've discovered, like Phoenix A and TON 618, push our theoretical models to their limits. We might be missing something fundamental about how black holes form and grow. That uncertainty is part of why studying them at every scale matters. Each new black hole we measure refines our understanding. Each merger detected by gravitational wave observatories adds a data point. Each photograph from the Event Horizon Telescope tests our prediction. The black hole catalogue is still being filled in. And meanwhile, the existing population of black holes continues to do what they've always done. They sit. They feed sometimes. They grow slowly. They warp time. They bend light. They wait. Let me close with one more image. Right now, in our galaxy, hundreds of millions of stellar mass black holes drift through interstellar space. Most are invisible, undetectable by any current telescope. They wander, dark and silent, between the stars. Some are alone, some have companions, none are bothering anyone. At the center of our galaxy, 4 million times the mass of our Sun is concentrated into a region smaller than 17 times our Sun's diameter. We've photographed it. We know it's there. It's been there for billions of years, since long before Earth formed, and it'll be there for billions more, long after Earth is gone. In the center of nearly every other galaxy in the visible universe, a similar object sits. Bigger or smaller, more or less active, but always present, always there, always warping the space and time around it. And out at the edges of the observable universe, the largest of these objects, the ultramassive ones, hold their galaxies together with gravity that bends light and slows time across light years. Consider what it means that we can study these objects at all. 100 years ago, we had Einstein's equations and Schwarzschild's solution, but no way to see whether black holes actually existed. 80 years ago, Oppenheimer's analysis suggested they should form when massive stars die, but the field was too distracted by global war to follow through. 60 years ago, we found Cygnus X1, the first candidate. 40 years ago, we knew the supermassive black holes existed at galactic centers, inferred from orbital dynamics. 20 years ago, we'd traced the orbits of stars near Sagittarius A star with extraordinary precision. 10 years ago, we detected the first black hole merger via gravitational waves. 5 years ago, we photographed M87 star. 3 years ago, we photographed Sagittarius A star. The field of observational black hole astronomy is barely older than half a century. The most spectacular results are from just the last decade. You are alive at the first moment in human history when we can directly observe black holes. Every previous generation of humans looking up at the night sky knew nothing of these objects. The galaxy was full of them then, just as it is now, but no telescope could detect them, and no theory predicted them. Aristotle didn't know, Galileo didn't know, Newton didn't know. Einstein, by the end of his life, knew the equations predicted them, but never lived to see one. You are part of the first generation that gets to look at them directly. There's something humbling about that. The objects have always been there. The universe has always contained these strange, dense, time-bending regions. We are simply the first humans to see them. Lie back, get comfortable. The universe is doing its strange work. Out there, right now, light is being swallowed. Stars are slowly spiraling towards central black holes. Time is dilating in the strongest gravitational fields we know about. The largest objects in existence are slowly growing, slowly turning, slowly waiting. Picture, for a moment, the journey of a single photon. Born in the heart of a distant star, it travels outward through stellar layers, eventually escaping into space. It travels for thousands of years, perhaps millions, perhaps billions, and one day, it crosses the event horizon of a black hole. From that moment forward, the photon is part of the black hole. It cannot leave. The mass of the black hole increases by an immeasurably tiny amount, equivalent to the energy of that single photon. The photon's history, the star that produced it, the path it traveled, all of that information is now hidden, perhaps forever, behind an event horizon. This is happening somewhere all the time. Billions of photons crossing event horizons every second across the visible universe, each one a tiny addition to the total mass of black holes, each one a small contribution to the slow, inevitable growth of the largest gravitational objects in existence. We are very small. The universe contains things that operate at scales we can describe but not really understand. And the strangest of those things, the densest, the most extreme, the most unknowable, are the black holes. Sleep well. The universe keeps its secrets. The black holes keep theirs. And the light keeps coming, even when the destination is one we can never see. Out there, the largest black holes are still slowly growing, slowly consuming, slowly anchoring the centers of distant galaxies. Stars are still being born and dying, some destined to leave behind black holes of their own. The cosmic web is woven through with these dark objects, connecting galaxies through their central monsters. Wherever there is mass concentrated enough, gravity does its work, and a black hole forms. The universe will continue this process for hundreds of trillions of years. New black holes will form. Existing black holes will grow through accretion and merger. Eventually, after even the longest-lived stars have burned out, only black holes will remain as visible objects in the universe. Then they too will slowly evaporate through Hawking radiation, until the universe is left with only background photons and a few escaped particles drifting in cooling space. Consider the timeline of cosmic history laid out before us. The universe is roughly 14 billion years old today, the age of stars, when ordinary stellar fusion produces most of the visible light in the universe, will continue for about another 100 billion years. After that, star formation slows dramatically. The smallest red dwarf stars can continue burning for 1 trillion years or more, but eventually even they exhaust their fuel. Then comes what some cosmologists call the degenerate era, when the universe is populated mostly by stellar remnants. White dwarfs, neutron stars, and stellar mass black holes drift through galaxies that have lost their bright glow. This era could last for 10 to the 39 years, trillions of trillions of trillions of years. The universe is dim during this time, lit only by occasional events. A stellar collision here, a black hole accretion there. After the degenerate era comes what's sometimes called the black hole era. Stars are entirely gone. White dwarfs and neutron stars have either decayed through proton decay, if proton decay actually occurs, or have been consumed by black holes through random encounters. The universe is populated primarily by black holes, ranging from stellar mass to supermassive, slowly drifting in expanding space. This black hole era could last for 10 to the 100 years, numbers that have no real meaning to a human mind. During this time, the largest black holes slowly grow by capturing wandering objects and by hawking radiation, cooling their environment. They also slowly evaporate through hawking radiation themselves, but the rate of evaporation is so slow that most of them persist for the entire duration. Eventually, even the largest supermassive black holes evaporate completely. The last black holes in the universe will be the ones that grew to the greatest mass during the active eras, perhaps similar in scale to TON 618 or larger. Their final evaporations, sometime around 10 to the 100th power years from now, will be the last energetic events in the universe before everything fades to background radiation and cooled photons drifting through space. That's the end of cosmic history in some models. Black holes are the last survivors. They are the longest-lived structures in the universe, outlasting stars by enormous factors. Tonight, we walked through their scale. Tomorrow, in cosmic terms, they'll still be here. Trillions of years from now, still here. The black holes outlast everything, but that is far in the future. Tonight, the black holes are everywhere. Tonight, they are doing what they've always done. Hundreds of millions of small ones drifting silently through our galaxy. A central monster at the heart of every galaxy you can see. The largest, the ultramassive ones, anchoring the cosmic structure of the most distant clusters. All of them silent, all of them waiting, all of them slowly turning in the dark. Good night, traveler. The black holes are still out there. The light keeps coming. Sleep well.